Hello everyone. If you are interested in meshless methods, then you have come to a right lecture tutorial. In this lecture, we are going to talk about a meshless method which is called Smooth Particle Hydrodynamics. Let's get started. The main purpose of doing this particular lecture series is to promote an open source software which is developed by my former research group at IIT Bombay. The name of the software is PySPH, as you can see here. And using this particular technique, SPH, you can simulate fluid dynamics, something like a free surface in which the surface of the fluid is open to the atmosphere. In smooth particle hydrodynamics, there are some benefits that you don't have to track the surface. The surface is automatically tracked by identifying different particles that are involved. You can also solve solid mechanics. So let's say there is a beam, and in finite element method you can only handle a small deformation of this particular beam, and if the deformation is large, then in that case the elements that you are using to solve this particular phenomena, they get distorted a lot. That makes the computation inaccurate. In meshless method, you don't have to worry about that, because the particles which are describing this particular metal rod, they adjust themselves such that this particular skewed element formation does not arise at all. This particular method was originally developed for astrophysics. Before diving deep into the SPH method, we'll first talk about what is interpolation, because at the base of any computational method we have interpolation. For example, if you are describing something using these elements, you do some kind of interpolation to get the value at each and every point, and in this way you can find what is the gradient and various other operator which act on this field. Let's say this is velocity. Therefore, interpolation is essential. In order to perform any interpolation, we have to assume a vector space. A vector space can be a polynomial space, and it can be a Fourier series, something like sine theta, sine 2 theta, cos theta, cos 2 theta, and it can be some other functions as well. They satisfy some properties in order to make sure that the interpolation is correct. That means you can assume something like this. Let's say there is a surface and you want to approximate this. You can approximate this using a bunch of straight edges. There is this curve and you can approximate this using a lot of edges. All these small edges is a vector space, and you can define this particular curve as a summation of some weight times these vectors. In this way, this particular curve, which is nothing but a function, it is projected onto these set of vectors, which is called the new vector space, and all these small vectors are called the basis functions. This is a very crude explanation. This is not mathematically correct, but this is what essentially happening when you are approximating an actual surface or an actual field which is continuous, which exists at each and every point by using some discrete points that you are putting in the computer and trying to manipulate and solve. This is how an approximation looks like. A function is nothing but a sum of product of the weights and the basis function. Some example of interpolation techniques are polynomial interpolation, Lagrange interpolation. This kind of interpolation is widely used in finite element methods. Then there is Fourier expansion. This is used in spectral methods. And then smooth particle hydrodynamics, which is also an interpolation technique. We'll talk about all of them, and we'll also do a little bit of coding to explain that how these different interpolation techniques are working, but this is not the main objective of this particular lecture. We'll briefly talk about the interpolation on a 1D function, and we'll then jump on to smooth particle hydrodynamics. Let's first talk about polynomial interpolation. A polynomial interpolation is done using, let's say you have a bunch of points, and for this bunch of points in X you have some values that you know. If there are, say, 1 2 3 4 5 6 points, then you can say that I'll use basis function 1 x x squared x cube x to the power 4, the number of points minus 1. In this case this will be 1 x x squared x cube x to the power x to the power 5. I'll write this directly. In this way you choose a basis. Your function is now, which is an approximation, is a0, which is a weight times 1, plus a1 times x plus a2 times x squared plus a3 times x cube plus a4 times x to the power 4 plus a5 times x to the power 5. If you want to visualize how they are going to look here, let's say this is 1, this is 2, and so on. Your first basis function is going to look something like this. Let me use another color. Your 1 function is this, your x is this, your x squared is something like this, x cube is something like, it's steeper than x squared. Similarly all other values. Clearly all the basis function, they exist everywhere. They have a non-zero value for each and every point. At this point you are going to find a weight such that the sum of this is equal to this value. Let me go to the next slide. What you are going to have is a0 times x1. x1 is the first point, which is this point. This is first point, this is second point, and so on. You will get a0 x1 plus a1 x1, a0 only. You will get only a0, then x plus a2 x1 squared plus a3 x1 cube plus a4 x1 to power 4 plus a5 x1 to power 5 is equal to, let's say this first point has a value y1. This should be equal to y1. Similarly you can write a similar equation, which is a0 times x2 and so on, a5 to power x to power 5 is equal to y2. So you will get 5 equations. Therefore you can write this in this format, where x1 1 x0 to power x power n goes here, and a0 to a1, which is common in all the rows, comes as a column matrix. You can write this in a matrix format, and on the right hand side you will get all the values that you know. This particular matrix is called van der Waals matrix or van der Waals system, and this particular system is hard to solve when this x values, let's say this is from 0 to 1, all these values are going to be less than 1. But if this is 0 to, say, 100 to power 5 is going to be a very large value. That is going to make this system very hard to solve. The diagonal values are going to be very large, and that becomes very hard to solve. There are some oscillations that you observe in the approximation when the degree n is large. Let's say you take the basis function 1x x squared and x to the power 100. When this is very large, then you should never go beyond -1 to 1 scale. If you even make this 1.1, then 1.1 to the power 100 is going to be a very large value, and that will make the condition number of this particular system very high. That means harder to solve. The remedies are as follows. You can have domain scaling. You can scale the domain, as I said here. You can always scale the domain to -1 to 1. You can use Chebyshev nodes. These nodes are the solution of a certain polynomial, which gives a nice set of values to the coefficients that you get here. And you can also use piecewise splines. That means your splines will not be effective for the entire domain. You can have a certain set let's say for this particular function you use a set of coefficient a0 to an, and then for this set you'll use another. This is the main principle behind the finite element method. We'll write a Python code where we'll use polynomial interpolation to interpolate a sine function. Let me open that. I have already created this particular file. First, let's import numpy. First of all, we'll create a function, monomial basis functions. We need the x value and the degree. We need for I in range degree plus 1. We need an array which we'll write as the basis. These are the basis, and basis is x to power this. Let me write just n here, right? So, and return the basis. Now what this function is going to do, it's going to return for a given position and the number of bases that I require. It will return, let's say for n equal to 3, it will return 1x and x squared. Now using this, I'll create a Monday matrix. Basically I'll need all the x values and I don't need n. I'll just create the Monday matrix for all the x values so that I'll always have a n cross n system. N is length of that, and v is, I'll populate it with all zeros, and then for all rows I'll use this function that I have created. Right, now I'll create x points equal to linspace from negative pi to pi. I'll create just 10 points, and then y points are the sine function. Using these points I want to create a matrix. My v is create all the x points. Now in order to solve this system I need to invert this. I have created this matrix, and in order to solve I can use this function. The coefficients is equal to, I'll take this matrix and the y points. These y points are the solution, the right hand side. Once I have this, I can write for any new point x, I can have the coefficients that I have generated here and get the value. My solution is this, which is a, which is the coefficient, a times x to the power 0 is 1, then a1 times x to the power 1, which is x, then a2 times x squared, a3 times x cubed, and so on. This depends upon the number of coefficients. Therefore n equal to the length of coefficient. Now I'll create a dense set of points in the same space. I'll take 100 points now, and now I'll use this function. These are the new points. On these points I'll use these coefficients which I calculated using only 10 points, right? Now let's plot them. Let me import matplotlib, import matplotlib splt, and then let's plot. These are the data points, and these are the actual interpolated polynomial, and this is the actual function, right? And let's also show this. Now let's run. So you can see here, let me also turn on the legends and grid labels as well, and y label is y. Let's again, here you can see these were the data points and I used 10 points, therefore the interpolation is very good, and this was the origin function. Let us just reduce the number of points. These are 10 points. Instead of 10, let's use only 4 points. So you can see with 4 points, the interpolation is not that accurate. This is the interpolating polynomial, and this is the actual function, actual sine function. And let's also do one thing, which is instead of 4 points, let's take 3 points. What will happen? The interpolation should be even less accurate. Therefore, let's see what happens. You can see the interpolation is all zeros, because as you can see the values that I have chosen is it's all zero. The interpolation is not getting any information at all. Therefore, you should make sure that you not do this kind of mistakes where you choose the sampling such that you always encounter these zeros. If this much is clear, let's jump to the next kind of interpolation, which is Lagrange interpolation. Here you notice that you have to find the coefficients a0, a1 and so on using the y values. But in Lagrange interpolation, Lagrange suggested that you can directly construct your basis functions such that you can directly use the coefficients, which is the value of the points itself. You can see the function, the approximation is equal to yi, which are the data we have, times these functions. The only effort that you have to put in is to construct these Lagrange bases, which are very easy. These are some of the properties of Lagrange interpolation, that it is exact at a given point. So you can see here that the Lagrange polynomial is constructed such that, let's say I have these 3 points. This is x1, x2, x3. These are the 3 points and there are some values associated with them. This is the actual curve. This is y1, y2, y3. For x1, I cannot consider x1 at all. My basis function will be x minus x2, and then here x1 minus x2 times x minus x3 over x minus x1 minus x3. So clearly this is my Lx. So that means this is a basis function which is a function of x, and if I want to compute Lx1, I'll get x1 minus x2 and x1 minus x2 in the denominator, so therefore this is 1 and the next one is also 1. At x1 I am going to get 1, and all other points, let's say x2, I am going to get this term 0, x3 this term 0. So my function will look something like this. At x1 I am going to get 1, at x2 I am going to get 0, x3 I am going to get 0. Similarly for this point I am going to get 1 here and 0 at these 2 points. My basis function will look something like this. Similarly for this point I am going to get 1 here and 0 at both the points. This I showed for just 3 points, but for more number of points it's going to oscillate a lot. Let's construct Lagrange polynomials and use that for interpolation. Here I have not used a very large number of basis functions. Let's try for polynomial basis if this is say 100, and here I am doing it for say 1000 points. Let's see what happens. This will create a very large matrix, maybe take time to solve as well. I did not save this. You can see there was still no problem. Let's change the function. Let me show you one function for which this polynomial interpolation fails, which looks very simple. It's 1 plus 25 times x squared. Yes, this is the Runge function, and here I'll use say 10 points first, and here 100 points. There was some problem here. I have to use this 1 over 1 plus 25 into x tens whole squared. You can clearly see that the polynomial interpolation fails, and even if you try to increase this, let's try to increase this number of points to say 30, it will even show more oscillations. You can see here. This can be fixed if you choose certain other points. These points were uniformly distributed. If you choose say Chebyshev points are this. Now let's try again. Let's try with 10 points. Let's see if this has a better accuracy here. Okay, I think the problem is because our interpolation goes beyond -1 to 1. So I'll use -1 to 1 like this and then do it. So you can see the interpolation is better. Now let me change this to 30. Clearly this is again better, and you can see that what it does is it takes more number of points close to the boundary, because close to the boundary these values, these increase. That's why the square of that is going to be a square, cube, and higher power are going to be very high. If you have more number of points close to these higher numbers, then you will have more chance to have better accuracy. Now we'll use these same points and same function, and now I'll create Lagrange polynomial, Lagrange interpolation. Let me create basis first, Lagrange basis function. This is how a Lagrange basis function looks like. For a given number of points, it will just take those points and then give you the basis function for a certain point x, right? This j is the point where you want to have this particular basis function, because for that particular point it is not considering that particular position in the basis function. That means when you skip that particular point, for that point you are constructing this basis. Now if this is clear, let's do Lagrange interpolation. I'll use this function. Now the interpolation is like this. You don't have to solve anymore. You directly take the points, the actual values of the y points, and use the Lagrange basis functions to get the value as y times the basis function and sum of all the basis functions. Now let me do that. I'll comment this. We don't need this and we don't need this one. Now our y dense is going to be x dense times x points and y points. The original points are required because these are required to construct the basis function, and these are the weight that is multiplied to the basis functions, and this is required to get the value at each and every point. This x value, this comes from here. You are creating all the values at one shot. There is no loop. Let's again run this, and there was absolutely no change that you can observe here, but the thing to note here is that there is no requirement to solve a linear system. You can directly construct this and then use that here. Now let's move to the next kind of interpolation, which is Fourier interpolation. There are some methods to mitigate the Runge phenomenon that we observed, and I already discussed this. So there are other kinds of points as well, which is called Gauss-Legendre point. We use this Chebyshev notes, which was this, and then these are the reasons why this works. Now we'll talk about this Fourier expansion. Fourier expansion is nothing but expressing this function f in terms of trigonometric functions. That means a0 plus a1 sine x, a2 cos x, plus a3 sine 2x, and so on. The basis function will look something like this. A is this, then sine x is this, then cos x is this, and so on. We will have higher and higher frequency of this particular basis functions. Let's try this. We'll manually construct these functions. First, we'll create Fourier basis. So for x, these are the basis function. You see from here, the first basis is 0, then sine, then cos, then sine 2x, cos 2x. Therefore, you have to do this kind of a trick where in an alternate fashion it chooses sine and cos. Let's use this basis function to create Vandermonde matrix for Fourier basis. Unlike Lagrange interpolation, you won't have these coefficients, and along with that there is one more drawback of this interpolation, is that the function should be periodic. If this function that you want to interpolate is not a periodic function, then you will not have a good result, because all the basis functions are periodic. Now using this, it looks like that it won't be able to interpolate this function, but here this particular function can assume that the pump is periodic. Let's see how it interpolates this particular function. We'll again create V for using the Vandermonde, the function that we just created, and then we calculate the coefficients. Coefficient is just solving this. Now we'll use the interpolation. Again, I have to create one more function which will interpolate this. Fourier interpolation is nothing but for coefficients, we have to do something like this. As we have done here, we have to alternatively choose the function in a similar manner that we have done here. If you change this pattern, then you have to use the same pattern here as well. Y tens is Fourier interpolation of this, and again let's try the interpolation. Clearly this also works, because let me just check if everything is fine. We changed this, we used a new interpolation, and clearly we are using the new function. Here, if we zoom near the peak, you can see that it is accurate here as well as here. And let's also try to do this without these Chebyshev nodes. This should be from -1 to 1, and now again try. So you can see that the behavior was different. It is different because this function is not periodic. This has some weird behavior here, but unlike polynomial interpolation, it does not show any kind of problems near the peak. Therefore, one of the benefits of this Fourier expansion is that it does not get affected by this Runge phenomena, and you can have higher and higher number of these basis function to have accuracy. Let me try 60. So accept this, I think accept the ends, because this is not periodic, we'll have a good interpolation at the peak. You can see here it exactly passes through this function. With this, we'll come to our main topic, which is the SPH interpolation. This is how you can get the coefficients, and this is how you get the function. And let's talk about the smooth particle hydrodynamics. So far, what we have seen is that all the basis function, constant, linear, x squared, x cube, so this is a constant x squared, x cube, all these, they had a non-zero value for the entire domain from 0 to infinity. So these are global functions. They have a non-zero value at each and every point. Similarly, for the Fourier basis as well, they are all global. They exist at each and every point. This is constant, sine, cos. And this particular function, which is the Lagrange basis, they had this particular property that within the domain in which they were defined, they had non-zero value, but they had a zero value at the points at which the other bases are defined, and away from the domain it can have any value. You don't have any control over that. These all, you can say, are global bases. They exist at each and every point. They have a non-zero value. But in the smooth particle hydrodynamics, you have local bases. You can also say they are stationary functions. At this point, you can have a function which is non-zero to a certain extent, and then it is zero everywhere else. Similarly, this is another basis, and this is another basis. And one more benefit of smooth particle hydrodynamics interpolation is that all these functions are just translations of a single function. You just translate it and you get another basis. And you can also scale it, divide by some h value, and you get a bunch of functions that you can use as basis functions to get an approximation of a given function. This is how a continuous approximation of any function looks like. This is the values that you know, and these are the basis functions. This is these translations, and this particular value is the scaling. Scaling can make the kernel thin or fat. This is the discrete form of this. This is similar to what we have seen so far. Fyi times Vj is the weight, and Wx minus Yj are the basis functions, phi. These are the advantages. This is local, as I explained, and it can handle large deformation and moving boundaries. These are the benefits of the SPH method as a numerical method. Let me show you in the code that how you can do it. Again, we'll use the same functions. Hopefully it will work for this Runge function as well. Let's see. These W functions can be anything. We'll use a Gaussian kernel, Gaussian basis function. This is how we are going to define this. This is the kernel. This is again the Gaussian kernel only, but it has some factor. This factor is this, which makes sure that the sum of this particular function at any point is equal to 1. Another benefit of SPH method is that it does not require a matrix inversion. You can do something like this function approximation. Dx, we are going to assume uniform points only, and it takes y times the kernel, and this times there should be a dx here. As in the presentation you can see, this is the function value, this is the kernel times vj, which is the volume. Volume is nothing but the distance between two interpolating points. Now let's use this. We have x values, y values, we have x dense, and now we'll use y dense is equal to function approximation x dense times this. This is adding for all the points. It takes the kernel values, even though it is taking all the kernel values, but this is equal to 0 for most of the points. And when you actually use this particular method to simulate something, then we can use a nearest neighbor search algorithm to identify the points that are close and ignore the points which are far away to make the computation faster. Let's run this and see if we get it correct. Clearly, it gave a very good interpolation without any presence of Runge phenomena that was observed in case of polynomial interpolation as well as in Lagrange interpolation. And one of the drawback of SPH method is that if there is a lack of support, then it does not perform well. Near the boundary for this particle, there is nothing on the left side. Therefore, the errors are high. Similarly, on the other side, all the points are uniformly distributed, you can see here. And let's try to decrease the number of points to 10 and see how it performs. You can see that the smoothness is affecting the approximation everywhere. Let's make it 30 and then see. With the increase of points, there was a better accuracy, you can see. And now we'll again make it, say, 60. We have already seen 60. Let's make it 100. Equal number of points in both for the interpolation as well as this. This does not matter, by the way. We can increase this to 1000 and now see. So you can see it is more and more accurate here as well. So with this, we have completed 4 types of interpolation techniques, and we have seen that all have a similar structure, but the basis functions that we use, they decide how it is going to behave during the interpolation. And in the next lecture, we will see that since all these basis functions have this x and they all are essentially continuous functions. For example, for polynomials, we had 1x x squared. All the basis functions are continuous functions, and you can find for any x value, you can find the value of these basis functions. Similarly, for Lagrange basis, we have this x here, and for Fourier basis, you have this x here, and for these kernels as well. Therefore, if you are interested in the gradient of any function, then you can just take the gradient of these basis functions and find the gradient of the field that you have interpolated. That is the benefit of interpolation. You can first interpolate the field and then use the basis function to find the operation of any operator, for example divergence, gradient, or Laplacian of the field, and solve any kind of phenomena that is essentially solving a partial differential equation. In the next lecture, we are going to talk about gradient and Laplacian approximation using the SPH method only. Whatever we discuss there, it is applicable for other interpolations as well. And then we'll solve one problem using the SPH method, and then we will talk about PySPH software, which is an open source software, and that provides a framework that you can use to simulate very involved phenomena, for example a dam break or multi-phase flows, by writing equations in a certain format which are very easy. And if you understand SPH, then you can easily write those equations and solve any kind of phenomenon. See you in the next lecture. If you like the content of our lectures, then please like, share, and subscribe. Thank you.